It is about 1880, inside the Hartford, Connecticut factory where Albert Pope's Columbia bicycles are being built, and an inventor named George A. Long is trying to solve a problem that should be embarrassingly small. Long is building a steam-powered tricycle. The engine is already the difficult part. 2 cylinders, a boiler, piping, fuel, water, controls, all packed onto a light road vehicle at a time when the automobile does not yet exist as an American industry. He can make the frame, he can make the engine, he can make the steering linkage. But at the top of the front forks, he wants a better kind of steering head, one that will turn on small steel balls instead of rubbing on plain bushings. And he cannot make the balls. The Smithsonian's surviving account of the machine records the problem almost casually. Long wanted to use small balls in the steering heads, like the ones that would later become normal on bicycles and motorcycles, but he was unable to make balls small enough, so the tricycle was built with plain bearings instead. Think about the industrial situation hidden inside that sentence. A man working inside the factory of America's leading early bicycle maker could build a functioning steam road vehicle, yet a handful of tiny round pieces of hardened steel defeated him. That is the story we are going to follow, not the invention of the ball bearing. Ball bearings existed before the American bicycle boom, and European makers had already shown what they could do. The bicycle's role was different, and in some ways, more important. The bicycle took a precision mechanism that could remain an expensive specialty in a machine shop and forced it into a consumer product. It demanded low friction, light weight, repeatability, adjustment, durability, and above all, quantity. A bearing that worked beautifully when a skilled mechanic made one was not enough. Bicycle makers needed thousands, then hundreds of thousands, then millions of bearing balls, cups, cones, races, hubs, pedals, and crank assemblies that could be produced cheaply enough to disappear inside an ordinary machine sold to the public. And that demand arrived before the automobile. Within 20 years of Long's failed steering head, American factories would be grinding steel balls specifically for bicycle bearings. A Cleveland engineer would build a company around anti-friction bearings and then use that company as a bridge into electric automobiles. A Connecticut doorbell maker would enter the bicycle business, develop a coaster brake full of steel balls, and grow into one of the largest bearing manufacturers in the world. Bicycle plants would become automobile plants. Bicycle machinists would become automobile machinists. Bicycle inventions would move almost unchanged into cars. The object that opened that door was not the engine, it was the wheel. And inside the wheel were balls. To understand why the bicycle mattered industrially, you have to forget what a bicycle looks like to us now. Today it is visually simple because a century and a half of refinement has made every part familiar. In the 1870s and 1880s, it was one of the most technologically provocative machines an ordinary person could buy. The United States had seen an earlier craze for the heavy wooden and iron velocipede, the so-called bone shaker. But that enthusiasm collapsed quickly. Roads were poor, the machines were uncomfortable, and American development slowed during the 1870s, while British and French designers kept improving the cycle. Then the Philadelphia Centennial Exposition of 1876 put advanced English high-wheel bicycles in front of American eyes. One of the men who understood what he was seeing was Albert Augustus Pope. Pope began importing English bicycles in 1877. In 1878, his Pope Manufacturing Company began building bicycles under the Columbia name at the Weed Sewing Machine Company factory in Hartford, Connecticut. The choice of factory matters. Sewing machines were already precision consumer machinery. Small shafts, rotating parts, hardened surfaces, castings, screws, jigs, gauges, and mechanisms produced in quantity. Pope did not begin bicycle production in a blacksmith shop. He inserted the new machine into an existing culture of repeatable metalworking. At first, the American bicycle still carried much of its European inheritance. High front wheel, direct pedals, solid rubber tires, a rider perched high enough that a stone in the road could throw him forward over the handlebars. But every season brought pressure for improvement. Better steel, lighter frames, better tires, more reliable hubs, more controllable steering, less friction. That last requirement was unlike the demands of a steam engine or a factory machine, because the bicycle had a brutally limited power source. The engine was a person. A steam engine can waste power and compensate with more coal. A gasoline engine can lose a few horsepower to friction and still move the vehicle. A rider has only a fraction of 1 horsepower to divide among acceleration, climbing, air resistance, tire losses, chain losses, and every rotating joint in the machine. Friction that would be a nuisance in a powered machine becomes something the rider can feel directly in his legs. That made the bicycle a ruthless test bench for anti-friction technology. The wheel hubs had to rotate freely while carrying the rider's weight. The crank had to turn under repeated pedal force. The pedals themselves had to spin under the rider's feet. The steering had to move lightly, but without dangerous looseness. Each of those joints presented the same problem. How do you support a load and allow rotation without forcing 2 broad metal surfaces to slide against each other? The old answer was a plain bearing, shaft against bushing, separated by oil if you were lucky. The increasingly attractive answer was to put rolling elements between them. This is where the bicycle became much more than transportation. It became a mass-market argument for precision. A ball bearing is simple enough to explain in one sentence. Instead of allowing 2 surfaces to slide across one another, you place hardened balls between them so that the surfaces roll. The reduction in friction can be dramatic, but the bicycle added a second advantage that mattered just as much. A rolling bearing could carry useful load in a compact, lightweight package. That is exactly what a bicycle designer wanted. Every ounce removed from the machine had to be accelerated by the rider. Every oversized bushing, heavy oil reservoir, and broad sliding surface was dead weight. The classic bicycle solution became the cup and cone bearing. One race, the cup is shaped into the hub, or a separate part. Another race, the cone, threads onto the axle. Steel balls run between the 2 curved surfaces. Tighten the cone, and you remove looseness. Tighten it too far, and the bearing binds. Back it off too far, and the wheel develops play. Set it correctly, and the wheel spins with almost no perceptible resistance, while the races keep the balls captured around the axle. That adjustability was especially valuable in an era when manufacturing tolerances were improving, but still imperfect. The mechanic did not need every component to emerge from the factory at one mathematically exact final dimension. He could set the running clearance during assembly and later compensate for wear. Precision and serviceability worked together. But the bearing only looked forgiving from the outside. The ball itself was merciless. If the balls in one bearing differed too much in diameter, the largest ones carried more of the load. If they were out of round, the bearing rose and fell microscopically as it rotated. If the steel was too soft, the balls and races dented. If it was too brittle, they could crack. If the surfaces were rough, the roughness became vibration and wear. Dirt entering the bearing turned lubricant into grinding compound. A bicycle hub therefore transformed a humble steel sphere into a precision product. And the sphere is an awkward product to manufacture. A lathe loves cylinders because a cylinder has an axis. A mill loves flat surfaces because a flat can be referenced. A sphere offers no preferred direction. Clamp it, and part of the surface disappears under the clamp. Reposition it, and the new cut has to blend into the old one. A craftsman can make something approximately round. Industry needs thousands of balls that are not merely round to the eye, but sufficiently round, hard, smooth, and equal that they can share load inside the same bearing. This was the gap George Long encountered around 1880. The problem was not understanding what the small balls would do in his steering head. The problem was producing the little objects economically enough and accurately enough to use them. Bicycle makers could import high-quality components, and early American cycles drew heavily on European practice. But import dependence becomes uncomfortable when the market begins to grow faster than anyone expects, and the market was about to become enormous. The high-wheel bicycle created enthusiasts. The safety bicycle created customers. By the late 1880s, the modern basic layout had emerged. 2 wheels of roughly equal size, a diamond-shaped frame, pedals driving the rear wheel through a chain, and eventually pneumatic tires. The rider sat lower. The danger of going over the front wheel was dramatically reduced, and the machine became practical for a much larger population. That change altered the economics of every component inside the bicycle. A high wheeler could remain expensive sporting equipment for a relatively narrow class of adventurous riders. The safety bicycle could become transportation. People used it to commute, to make deliveries, to visit friends, to tour, to race, and simply to escape the radius of life that could be covered on foot. Women adopted the bicycle in large numbers, making it part of a broader transformation in personal mobility. Clubs multiplied. Racing became a major sport. The League of American Wheelmen grew into a national organization with enormous political influence on the good roads movement. The production figures show the scale of the change. Smithsonian historians estimate American bicycle output at about 200,000 machines in 1889. By 1899, production had risen to about 1 million bicycles a year. 1 million bicycles is not 1 million simple frames. Each machine is a bundle of precision rotating joints. 2 wheel hubs, a crank or bottom bracket assembly, pedals, often ball-supported steering components, and accessory mechanisms. Even if designs differed, the industrial implication was unavoidable. The bicycle boom demanded balls and races by the millions, and it demanded them at consumer prices. This is the point where the bicycle did something that a machine tool, a railroad axle, or an expensive scientific instrument could not do in quite the same way. Those applications could justify specialized maintenance and high component costs. The bicycle market punished both. A bicycle had to leave a factory, go to a dealer, be purchased by someone who might know almost nothing about mechanics, survive rough roads, rain, dust, bad lubrication, careless adjustment, and thousands of revolutions, then be repaired by a local shop rather than returned to its maker. The component, therefore, had to become not only precise but ordinary. That is one of the most powerful forces in industrial history. A technology often becomes economically important, not when someone proves it can work, but when a mass market forces manufacturers to make it cheap, interchangeable, repairable, and abundant. The bicycle was doing that to several technologies at once. Steel tubing became lighter and better controlled. Wire wheels improved. Roller chain became a sophisticated precision product. Pneumatic tires became commercial necessities. Metal stamping, brazing, forging, heat treatment, and surface finishing all improved under competitive pressure. Ball bearings were part of that same package. And the pressure did not come only from buyers who wanted an easier ride. It came from racers who wanted to go faster. The bicycle industry of the 1890s lived in a culture obsessed with speed. Racing heroes were national celebrities. Manufacturers advertised competition results. Riders attempted distance records, endurance records, and paced speed records behind trains and motor vehicles. In June 1899, Charles "Mile a Minute" Murphy famously rode a bicycle behind a locomotive on a specially boarded stretch of Long Island Railroad and covered a mile at a little over 60 miles per hour. Stunts like that were spectacular, but the industrial pressure behind them was serious. A racing bicycle is a machine in which tiny losses matter. A rough bearing does not merely make noise, it consumes part of the rider's limited output. A heavy hub does not merely increase shipping weight. It has to be accelerated every time the rider changes speed. Poorly fitted balls create drag. Badly hardened races pit. A bearing that loosens changes wheel alignment. A contaminated bearing can turn a fast machine into a grinding machine. The Smithsonian's History of American Cycling notes that the demand for lighter and faster bicycles accelerated improvements by manufacturers. That competitive environment rewarded the companies that could make bearing surfaces smoother, balls more consistent, hubs lighter, and adjustments more reliable. It also taught consumers to care about hidden mechanical quality. Bicycle advertisements of the period repeatedly called attention to bearings. Ball bearing became a selling phrase because buyers understood that it meant lower friction and better construction. Trade journals discussed hubs, pedals, bottom brackets, bearing adjustment, lubrication, steel quality, and new bearing arrangements with a level of seriousness that would seem extraordinary if we still imagined the bicycle as a toy. The bicycle owner also became mechanically literate in a very practical way. He or she learned that a cone could be too tight, that a wheel needed to spin freely without side play, that bearings needed oil, that a rough feeling in a hub signaled trouble. Shops needed replacement balls, cones, cups, and tools. Dealers needed components from multiple suppliers. Manufacturers needed parts that could be produced in large batches. In other words, the bicycle created not only demand for bearings, but a culture that recognized bearing quality. That matters because industries grow faster when a component stops being an obscure internal detail and becomes something customers are willing to pay for. Once ball bearing becomes a feature printed in an advertisement, manufacturers have a reason to compete on it. Once hundreds of bicycle makers compete on it, suppliers have a reason to specialize. By the end of the 1890s, that specialization was visible in the most literal way possible. There were factories whose business was simply making the balls. In July 1900, a Maine newspaper reported that the plant of the Hathorne Manufacturing Company in Brewer was idle during a labor dispute. The description of the plant is more important than the dispute for our story. It ground steel balls for bicycle ball bearings, a factory for balls. That is how far the industry had moved from George Long's difficulty 20 years earlier. The bicycle supply chain had become deep enough that manufacturers did not have to make every component under one roof. One company could specialize in hubs, another in pedals, another in chains, another in spokes, another in tires, another in steel balls. Trade publications of the era are full of advertisements from firms selling parts to bicycle makers rather than finished bicycles to riders. This division of labor was a sign of maturity. Specialization allows a supplier to justify equipment that would make no economic sense for a small bicycle factory. A ball maker can invest in heading machines, grinding equipment, heat treatment furnaces, sorting methods, and inspection tools because every bicycle producer becomes a potential customer. The machine runs all day, making one family of parts. Workers become familiar with one process. Scrap teaches lessons. Gauges improve. Tooling is refined. The cost per ball falls while consistency rises. And once that capability exists, nothing about it says the balls must remain inside bicycles. That is the crucial transition. The bicycle created an early mass market for small, efficient rolling bearings. But the same ball that reduces friction in a bicycle hub solves a general mechanical problem. Change the size, the race geometry, the steel, the load rating, and the bearing can move into a carriage axle, an electric motor, a machine tool, a pump, or an automobile. A supplier serving bicycle factories therefore possessed something more valuable than a bicycle business. It possessed process knowledge, how to harden steel without ruining it, how to grind spherical surfaces, how to finish raceways, how to control size, how to inspect quickly, how to produce thousands of nearly identical pieces rather than one beautiful piece, how to sell those pieces into a network of manufacturers who expect delivery on schedule. This is where industrial capability actually accumulates, not in one patent and not in one heroic invention, but in the repetition of a process, until the factory can do cheaply what an earlier craftsman struggled to do at all. In Cleveland, one engineer saw that the bearing itself could become the center of a business. His name was Walter C. Baker, and within 3 years, his bearing company would help create an automobile company. Walter C. Baker belonged to the generation that did not see a hard boundary between bicycle engineering and automobile engineering, because in the 1890s, that boundary barely existed. In 1895, Baker helped organize the American Ball Bearing Company in Cleveland around an anti-friction bearing of his own design. The company sold bearings to bicycle and carriage manufacturers. That customer list tells you exactly where the technology stood. The bearing was already escaping the bicycle, but the bicycle industry was one of the markets large and demanding enough to support a specialized bearing company. Baker did not stop at bearings. In 1897, he worked on an electric automobile, and in 1898, he helped organize the Baker Motor Vehicle Company. The sequence is almost too perfect for this story. ball bearings, then automobiles. The later Baker Electric became one of the best-known early electric car manufacturers in the United States. This was not a coincidence unique to one man. Cleveland's industrial history is full of the same migration. The city's bicycle industry expanded rapidly in the 1890s. More than a dozen important bicycle companies operated there. Names associated with Winton, White, Peerless, Lozier, and others later appeared in motor vehicle manufacturing. The historic American engineering record, looking back at Cleveland's industrial development, makes the connection unusually direct. The skilled labor and mechanical knowledge needed by the early automobile industry came substantially from carriage and bicycle manufacturing, and the bicycle companies in particular invested heavily in machinery and developed technologies that transferred naturally into motor vehicles. Alexander Winton is a good example. His bicycle company built thousands of machines, and his patents included work on ball and roller bearings. When the automobile emerged as the next mechanical market, Winton moved into it and became one of America's important pioneer car manufacturers. The transfer was not merely a matter of entrepreneurs changing the sign over the door. A bicycle factory already understood lightweight rotating machinery. It already bought seamless or drawn tubing, chains, sprockets, hubs, bearings, fasteners, rubber tires, and precision machine parts. It already had lathes, drills, presses, brazing equipment, jigs, inspection tools, and men who knew how to use them. It already knew how to assemble a machine from standardized components and sell it through a dealer network to ordinary consumers. An early automobile needed almost the same industrial vocabulary, only enlarged and complicated by an engine. That is why the bicycle should be understood as one of the automobile industry's workshops before the automobile industry existed, and bearings sat directly in the middle of the transfer. A car required far more of them, under far higher loads, at higher speeds and temperatures. But the American industry did not have to begin from zero. The market had already spent a decade paying companies to learn how rolling contact behaved in the real world. Then a second company demonstrated the same transition from an even more unlikely starting point. It began with doorbells. In Bristol, Connecticut, Albert F. Rockwell and his brother Edward established a business in the late 1880s, making an improved mechanical doorbell. The company became known as the New Departure Bell Company. Nothing in that origin sounds like the beginning of a bearing empire, but Bristol was a manufacturing town, and the Rockwells were willing to follow markets. When the bicycle boom arrived, a doorbell company already had some useful habits: small metal parts, springs, mechanisms, stamping, assembly, and consumer hardware. Bicycle accessories were a logical expansion. New Departure made bells for bicycles, which kept the company near the trade. Then it moved into a much more consequential product. In 1898, the company introduced a bicycle coaster brake that used steel balls to reduce friction. The coaster brake solved a problem every rider immediately understood. With a conventional fixed arrangement, the pedals could be mechanically tied to the wheel's motion. A freewheeling hub allowed the bicycle to coast while the pedals remained still, and integrating a brake into the rear hub created a compact mechanism that could be controlled by backpedaling. Inside that hub, however, simplicity disappeared. A coaster brake is a miniature transmission and brake assembly living in the center of a wheel. It contains rotating and stationary parts, clutches or screw mechanisms depending on the design, brake surfaces, an axle, a shell, and bearings that must allow the hub to rotate freely in normal riding while surviving torque during braking. Dirt and water attack from outside. The rider expects the mechanism to function for years. This is precisely the kind of product that turns a company from a general metalworker into a precision mechanism manufacturer. According to Preservation Connecticut's industrial history, New Departure's entry into bearing manufacture began with that 1898 bicycle coaster brake. From there, the company's involvement accelerated. The bicycle did not merely buy bearings from New Departure. The bicycle forced New Departure to become a bearing company. The chronology is remarkable. In 1888, Rockwell was making clockwork doorbells. A decade later, the company was producing a bicycle mechanism whose performance depended on steel balls. Within another decade, it was supplying bearings to automobile manufacturing. And within a generation, it would be producing ball bearings at a scale that would have sounded impossible when George Long was struggling with his tiny steering head balls in the Pope factory. This is the industrial path the title of this story is really about. Not bicycle equals bearing, as if one invented the other, but bicycle demand pulling unrelated American metalworking firms into the discipline of precision rolling contact. Once pulled in, they did not stay bicycle companies for long. There is a deeper reason the bicycle had this effect, and it has nothing to do with fashion. The bicycle was one of the first modern consumer machines in which precision could not be hidden behind brute force. A farm wagon could tolerate play. A heavy carriage could use large plain bearings and grease. A stationary machine could be massively built and bolted to the floor. A bicycle had to be light enough for a person to propel, strong enough to survive potholes, efficient enough that the rider did not feel every loss, and cheap enough to sell in a competitive market. Those constraints collided at every rotating joint. Make the bearing surfaces large and heavy, and the bicycle gains weight. Make them too small, and contact stress destroys them. Make the clearance too loose, and the wheel wobbles. Make it too tight, and friction rises. Use soft steel, and the race dents. Use hard steel, badly heat-treated, and it cracks. Machine the cup inaccurately, and the balls do not share the load. Let dirt in, and the race becomes a grinder. That is why the bicycle was such an effective school for manufacturing. It punished sloppy work immediately, but it did not offer the price margin of a locomotive or industrial machine. The solution had to be good and cheap at the same time. The industry learned to move skill from the craftsman's fingers into tooling and process. A bearing cup should not depend on a genius machinist feeling when it was right. A cone should come from a machine close enough to dimension that assembly required adjustment, not hand-fitting. Balls had to be formed, hardened, ground, finished, and sorted in batches. Gauges had to tell inspectors when parts crossed a limit. Fixtures had to make repetitive operations repetitive in fact, not only in theory. This is the same logic that would later define American automobile production. The bicycle also trained industry to think in sub-assemblies. A bicycle maker could buy a hub from one specialist, chain from another, tires from another, pedals from another, and build a finished machine whose parts came from an industrial ecosystem rather than one vertically integrated shop. That forced drawings, dimensions, thread standards, quality expectations, and purchasing practices to become more disciplined. A bearing supplier benefited enormously from that arrangement because it could serve many makers at once. Every improvement in grinding or heat treatment could be spread across thousands of bicycles from different brands. The bicycle industry became a network, and the bearing maker sat at a useful node inside it. Then the bicycle boom cooled. Normally, the decline of a market destroys industrial capacity. Here, something more interesting happened. The machines, workers, suppliers, and ideas looked for somewhere else to go. The automobile was waiting. The bicycle boom reached its great 1890s peak and then settled as the century turned. Companies failed, merged, diversified, or searched for new products. But a factory is not erased when demand for one product falls. Its lathes remain bolted to the floor. Its presses remain under belts and shafts. Its toolmakers still know how to build fixtures. Its machinists still know how to hold close dimensions. Its purchasing department still knows who sells tubing, chain, bearings, wire, and rubber. That accumulated capability became a launch platform for the automobile. The evidence is especially clear in Cleveland. Historic engineering research on the city's early auto industry found that many bicycle makers became motor vehicle makers, and that early automobile manufacturing methods closely resembled the bicycle and carriage methods that preceded them. The Winton, White, Peerless, Lozier, and related industrial families did not enter a completely new universe when they began building cars. They enlarged the machine and added new systems. The bicycle had already normalized a surprising amount of automotive anatomy. Wire spoke wheels were familiar. Pneumatic tires were familiar. Steel tubing was familiar, chain drive was familiar, ball bearings were familiar, lightweight steering mechanisms were familiar, sprockets, pedals, hubs, freewheels, and brake mechanisms had taught designers to package motion into small spaces. Even the culture of rapid product improvement transferred. Bicycle catalogs changed quickly, racing exposed weaknesses. Competitors copied good ideas. Patents multiplied. Customers expected a better model next season. That rhythm looked much more like the coming automobile business than the older carriage trade did. The bicycle therefore contributed two different things to the car. The obvious contribution was hardware. The less obvious contribution was industrial habit. A company accustomed to producing thousands of lightweight mechanical products for consumers was psychologically and technically prepared for a powered vehicle market in a way that a custom carriage builder was not. It understood that volume mattered. It understood dealer networks. It understood part supply. It understood model differentiation. It understood that a buyer cared about both performance and appearance. And when engineers increased the loads from bicycle scale to automobile scale, rolling bearings became even more attractive. Cars placed rotating shafts everywhere. Wheels, transmissions, engines, generators, differentials, steering gear, pumps. Some applications continued to favor plain bearings. Others used ball or roller bearings. The important thing is that America now possessed companies that understood rolling bearings as a manufacturable product rather than a foreign curiosity. One of those companies, New Departure, followed the automobile market so successfully that General Motors eventually absorbed it. The numbers show how complete the transformation became. New Departure's move from bicycle components into automotive bearings accelerated in the first decade of the 20th century. A Bristol engineering subsidiary organized in 1907 made automobiles, and New Departure supplied the kind of rolling bearing capability that the new vehicle industry increasingly demanded. Then came consolidation. In 1919, General Motors acquired New Departure. The bicycle-era company became part of one of the largest industrial corporations in the world. But it did not disappear inside it. It continued making bicycle parts while supplying bearings to automobile manufacturers. At full capacity, according to the documented industrial history of its Bristol works, New Departure employed roughly 7,000 people and produced about 225,000 ball bearings per day. Stop on that number, not balls. Bearings. 225,000 completed ball bearings in one day from a company whose route into the field had begun with a bicycle coaster brake in 1898. The scale is the answer to George Long's problem turned inside out. Around 1880, small balls were difficult enough that he abandoned the desired steering head design. A few decades later, Connecticut factories were organizing precision production on a scale measured in hundreds of thousands of bearings per day. New Departure was not alone. Fafnir, founded in nearby New Britain in 1911, entered the market with the explicit challenge of producing high-quality ball bearings domestically. The Torrington Company, Marlin Rockwell, Norma Hoffman, and other firms built a dense regional industry. During the 1920s and 1930s, New Departure and several other Connecticut bearing makers together produced more than half of the world's ball bearings, with New Departure described in the industrial record as the world's largest producer. The geography is striking. The American bearing industry did not arise in one giant government arsenal built for war. Much of it grew in the same Connecticut manufacturing belt that had produced clocks, guns, sewing machines, hardware, and bicycles. Each product left behind skills that the next product could reuse. The bicycle was unusually important because it brought precision rotating hardware into high-volume civilian production just before the automobile created an even larger demand. By the time cars began multiplying, America no longer had to ask whether consumers would pay for low-friction precision. Bicycle buyers had already done that experiment. The car industry scaled the answer. Then electric motors, machine tools, trucks, aircraft, and military production multiplied it again. But before we give the bicycle too much credit, there is an important correction to make, because ball bearings did not begin with bicycles. and American bearing history had other roots. Understanding those other roots makes the bicycle's actual contribution clearer, not smaller. The bicycle did not invent rolling contact, and American industry did not suddenly discover bearings in the 1890s. Ball and roller bearings existed in machinery before the bicycle boom. European manufacturers were already advancing the technology, and the United States developed other bearing traditions as well. Timken, for example, grew from the problem of carriage axles and tapered roller bearings rather than bicycles. The bicycle's contribution was more specific. It made precision rolling bearings a mass consumer requirement unusually early. A locomotive or machine tool could justify expensive specialist parts and skilled maintenance. A bicycle could not. Hundreds of makers were competing to sell lightweight machines to ordinary people. Their bearings had to be efficient, durable, adjustable, replaceable, and cheap enough to disappear inside the price of the finished bicycle. That combination, quantity, low price, and precision, created a market large enough for specialist suppliers, ball grinding plants, new bearing designs, repair parts, better heat treatment, and increasingly disciplined inspection. And the timing was almost perfect. Just as the bicycle market was creating that capability, the automobile arrived with a much larger appetite for rotating parts. The bicycle was not the birthplace of every American bearing. It was the bridge that helped carry precision rolling bearings from specialist machinery into mass transportation. Industrial history loves the first patent and the first inventor, but a patent does not create an industry. One perfect bearing does not create skilled grinders, heat treatment practice, gauges, suppliers, repair networks, or factories capable of making 10,000 more that behave the same way. Repeated production does. The bicycle kept ordering the product. Every production run taught factories something. Racing punished friction. Rough roads exposed weak hubs. Dealers reported failures. Repair shops revealed what wore first. Competing manufacturers forced suppliers to improve quality while lowering price. That feedback turned bearing knowledge into bearing capability. When bicycle demand softened, the capability remained. Machinery, toolmakers, inspectors, suppliers, and engineers who understood lightweight rotating mechanisms. In cities such as Cleveland, that industrial base moved directly into motor vehicles. The automobile therefore inherited more than bicycle parts. It inherited a trained manufacturing ecosystem. Steel tubing, wire wheels, pneumatic tires, chain drive, precision hubs, and ball bearings were already commercial technologies before the American car became a mass product. The engine was new. Much of the industrial language surrounding it was not. Go back to Hartford around 1880. George Long could build a functioning steam tricycle, but when he wanted tiny balls for improved steering head bearings, he could not make them small enough and used plain bushings instead. 20 years later, American factories were grinding steel balls specifically for bicycle bearings. Walter Baker had turned anti-friction bearings into a Cleveland business and then moved into electric automobiles. New Departure had followed bicycle bells into a coaster brake, followed the brake into bearing manufacture, and would later become part of General Motors. Bicycle companies in Cleveland carried their machinery and mechanical knowledge into the new automobile trade. And in Connecticut, bearing production eventually reached hundreds of thousands of completed bearings per day. The bicycle did not invent the ball bearing. Its achievement was to make the bearing ordinary. A bicycle gave precision rolling contact a mass market before the automobile existed at scale. It forced factories to make low friction, cheap, repeatable, serviceable, and abundant. Once those factories knew how to do that, the same knowledge did not stay inside bicycle hubs. It moved into cars, electric motors, machine tools, trucks, aircraft, and eventually the industrial machinery of a modern economy. That is why the mature bicycle is so easy to underestimate. It looks simple only because generations of difficult engineering have disappeared into expectation. The wheel should spin freely, the pedal should turn, the hub should last. Nobody riding the machine should have to think about the hardened steel balls carrying the load. Around 1880, those little balls could still stop an American inventor. A generation later, they were an industry. Before America put the world on wheels with automobiles, It learned one of the essential technologies of low-friction mass production on two wheels first. The bicycle did not merely carry Americans into the modern age. It helped teach American industry how to roll,